Steve. I would like to thank you again for inviting me at Stanford. So I am Murad Bouache. I work at Verizon. Before it was Oath and then Yahoo. I joined Yahoo in 2012. I'm going to talk about also the performance career too, which is my life. Also how you can live, of course, your social life, but with performance as well, because you see it even outside, in real life, not only at work. I did research also for performance, so it was my starting when I was doing my PhD in computer architecture. So I think the good news, Steve already announced it. So the good news is you are going to win. Actually, are we going to do a raffle or just the most interactive?
Maybe I like that, the most interactive.
The most interactive. The guy who's going to ask questions and answer to questions, because I have actually questions for you. Some of them, they are kind of basic questions. Some of them, they are kind of a little bit smart questions about performance, I promise. So this is a neural network stick, and I am using actually this. This will be in Linux or Windows, and then you can do inferencing for your model, neural network model, anything. It can be for performance. We are going to see how we can mix between artificial intelligence or deep learning with performance engineering. The second thing, so for everyone, is going to be Intel want to give you a 1-year license for the Parallel Studio. The Parallel Studio is like different packages actually. One of them, which is very related to performance, and it's the Intel vTune. But you can find the Intel compiler, optimized, different things that you can use for performance. So this for the most interactive guy or person, and this for everyone. Let me start my presentation. I'm going to talk a little bit about myself right now. So I got my PhD in computer architecture, especially in microarchitecture, in 2010 in the University of Perpignan in France. And then after this, I did several postdocs, one in France, in Paris. Another one, it was my first time, I think my second time in the US, in Champaign, Illinois, in University of Champaign, Illinois. I was doing compiler design there. So compiler design very connected to microarchitecture. And then I went to Waterloo, to University of Waterloo in Canada, to do embedded system instrumentation. And this is all about performance for research, or research of performance. And the difference is I saw a lot of software. I was doing a lot of software during, not only in my PhD, but also in my master's degree before. I was doing this in University of Boumerdès in Algeria, and before moving to France. And then, so 80% of software and a little bit of hardware. I think the only explanation is that we didn't have access to the hardware. Labs and universities in France, they don't have this ability to touch things, to touch the hardware, because they don't have enough money to buy all these supercomputers, HPC devices. When I landed here in Silicon Valley in 2012 at Yahoo, at that time we had 35 data centers. So I had access to all these data centers, not to play, but doing optimization. And it was my first corp job, and they saw that it's actually moving from software to hardware. At like 45%, 55% of my time was mostly hardware performance. And then Oath, Verizon after this, where we moved from 35 data centers to 6 data centers. So who is going to answer why we moved from 35 to 6? What's the, yes?
If the data centers themselves become more efficient.
Okay, efficiency, that's good. Any other guess?
Better telecommunications, better telco links.
You don't have a right to answer. You are in HP. I know you are working with us in data centers. Who is going to tell me another? Efficiency is one. Second thing? Yes?
Did you move some of your operations to the cloud?
Virtualization, that's good. Yeah, efficiency, virtualization, and also optimization. So performance engineering. So we did a lot of optimization through performance engineering. So just to tell you about the performance career is this interaction between software and hardware. Always working in software, optimizing software to get some optimization in hardware. there's always this interaction. So people who want to really move to performance career, it's all about this interaction between software and hardware. Let's return back a little bit of my background. This book was the book that I was really, it's a reference in microarchitecture. The name is Architecture des ordinateurs. It's in French. John Hennessy and David Peterson. And it's the same edition. It's just a translated copy, computer architecture. This was like really the CPU performance, memory performance for people who are preparing or doing research in computer architecture. And for me in 2003, it was like, oh, these guys are the reference. They are the pioneer of microarchitecture. So when I moved here in 2018, I was actually a guest also in a Facebook at Scale conference. I met this guy, and you cannot believe I was really, really excited. Like, this is the guy. This is the guy who's, and his presentation was like a new golden age for computer architecture. It was amazing presentation, like talking, like he's just telling what's the future of microarchitecture, what's the future of performance. Because when we talk about performance, we talk about different components in the server, but essentially about the CPU, memory, which is very connected. The rest is going to be I/O. We are going to see all these details later. And then guess what? I bought a book of leadership because in my job doing performance engineering and then after this doing management, I was looking for like a book who's going to help me really in management and leadership. And there, I bought this book, John Hennessy, and guess what? I got a signed copy. So he signed my book in 2019. It was here in Stanford. And the two pioneers now, like I met them, I took a picture, I took a selfie with them. It's really inspiring for the performance career, even for the future. Okay, let's talk about the agenda today. I'm going to talk about performance. What's the difference between benchmarking and profiling? A lot of people they have this, they are confused. What's benchmarking? What's profiling? Of course, hardware performance is going to be part of the agenda. We cannot talk about software performance without talking about hardware performance. Hardware is going to be the software, the CPU, memory, network, I/O performance. Of course, the next generation of the GPUs, FPGA, and we see a huge, like exponential increase of using this intensive compute devices or accelerators. Software performance, essentially Java application. Why Java application? You see why. We also see a lot of like a huge increase of Java usage in from developers. Mobile performance, mobile. Everyone talking about the mobile. So the most important thing is power and speed. We are going to talk about what are the tools that we can use to profile the mobile performance, especially for power and speed. Cloud performance, scale out the performance, and how we can use artificial intelligence and performance engineering at the same time. Because it's it's very possible. And actually, I wrote a paper for a conference, and it's going to be kind of unique how we can mix between two words of artificial intelligence and performance engineering. And then I'm going to give you what are the requirements for the best performance engineering job. So this is the Yahoo ecosystem. I know that people, some of you guys, you have email in Yahoo, and you always imagine how where is your email box, where is the server, and how we can connect from how you can connect from your home to this ecosystem. And the ecosystem is actually a bunch of data center, storage, cloud, and you can see the user can connect through internet. We are not going to talk about the performance of user because we don't have this control about his computer and also his network. We are just going to talk about going in or the access to our ecosystem inside the Yahoo, which is a bunch of servers, data centers, which we call highway, the cloud, storage, ad servers, all these things. So as you can see, this is the sign of performance. As you can see, we care about performance in every piece of this ecosystem. If we zoom in, in this ecosystem, you can see the data center, the highway. This is a beautiful picture how you can take the data from the grid, which is mail or this big data, taking them in a highway and then use them. The application is going to use this data. And then you have the platform services, the ad server, you have the storage here, local storage, you have the cloud, and you have the local storage and other way. So if you zoom in, you see also the performance is also present everywhere. And we have even real issues that we fixed in every piece in this ecosystem. Now, if we jump to software performance, same thing. You have every language, every programming language. We have a tool that we can profile and then optimize and try to make it even better. The two metrics that we care about at Yahoo is latency, which is the biggest enemy of Yahoo. And the second thing is the QPS, or how many queries per second, how many requests per second we're interacting with the database, either the grid, the big data, or even different other databases that we are interacting with. So we care. The performance is going to, or the performance engineering group is going to support every piece in either the application or the rest of the ecosystem of the rest of the world within Yahoo ecosystem. This is my group. My group is the performance engineering group. It's driving the next generation. If we are talking about the hardware review, we do everything which is hardware certification, hardware evaluation. For example, we have HP, for example, here. We talk to HP and see what's the best configuration that we can use with any application that we have. R&D, we have research and development, where we see the next generation of the technology, always looking for a new GPU, a new FPGA, new server, new type of server, new CPU, and so on. TCO model is about the total cost of ownership, which means that we don't only care about the cost, we care about performance related to the cost, the cooling, the power consumption, and also the maintenance of every server we have in our data center. The 6 data centers, sometimes we do a retirement where the technology is very old and then the application, there's some update in the application. So we try to do some refresh of different application and also the hardware. Infrastructure lab, we have a lab where we test all our, our optimization tools, also the technology. And this lab, we do the hardware certification as well. Within this lab, we do the performance benchmarking for data mining and analysis. This is actually, we are thinking more about how we can use our data, not only for performance, but also the data, the utilization data, or CPU, for example, the utilization, memory utilization, and how we can understand if there's some anomaly or create some anomaly detection through the data we have. So we have the server utilization, server optimization, hardware scanning, and system anomaly reporting, and the infrastructure planning. Okay, this is part of the performance engineering group mission to improve performance and efficiency and to reduce the cost in different layers. Our architecture, or a Verizon architecture, the code where we do optimization for different application, infrastructure, and hardware in general. Okay, what's performance study tell us? Just to try to find kind of a definition of performance. Why is some hardware better than others for different programs? So here we are going to talk about the hardware, specifically the CPU. Why you have two, for example, computers at home. One is faster than other. If we talk about the CPU, why some application is running or executing faster than other application in different machine. This is performance, or what are the factors of system performance related to the hardware? Do you need some new hardware? Do you need a new machine? For example, we always ask these questions, even in reality. And then if we go deep on the CPU, what are the instruction set? Why? For example, Intel is creating a new microarchitecture. Why we have this tick-tock cycle in Intel architecture. So optimizing for performance. So everyone is going to ask, okay, Murad, how you are going to tackle this issue of performance when you are at work. What are the steps? How you fix? What's your daily job? So when, for example, we have a performance issue, so this performance issue is sometimes it's kind of project where we are involved with the team, with developer, for example, Yahoo Mail, and then, or sometimes they just report the problem for us, and then we just start asking questions before to do anything. So first thing, do not harm. This is the first step. Just ask question, and then the more experience that you have, the best, because sometimes you just repeat the same thing for specific application. So the first thing we do is determine if this issue is a hardware or a software. If it's and between us, the hardware issue is much easier than a software because kind of static thing. Sometimes you just replace the component and then it's working. But with the software, it's really, really hard because you have a lot of things that can change. Sometimes people, they are reporting that, okay, I did the update in Friday and by Monday, the performance is horrible. So how can we solve this problem? So the software issue is more complicated. This is why I started with the software issue. But usually when we have a software issue, we do ask questions, but we do after this the code analysis or profiling, understand where is the issue. And the code profiling is going to be through different tools. Sometimes we use in-house tools. Sometimes we use like Intel vTune, for example, which is Intel product. We go with the simple, tools that just to profile to the complicated. What does it mean, simple to complicated? Simple, there's no overhead. You just see things, you monitor. And complicated, you do instrumentation. When you talk about instrumentation, means that you are adding things on your system, and then you have overhead, which is a little bit complicated. Sometimes you find yourself profiling your profiler. It's funny, but I saw it a lot. The hardware issue, which is simpler compared to the software, but usually we try to reproduce the issue. This is the next step, and then try different solutions. As I said, sometimes the framework, sometimes memory, sometimes the CPU, disk, network, different component on the server. Now, when we are done with both, and find the solution, we validate on the production, because usually this issue, usually it's in the production, and then you have really like 10-15 minutes to solve a problem. If not, then you are losing a lot of money. And then you feel, I don't know how to, should I exit from here, or because it's bothering the text? Yeah, this is stop screening.
I think you can just click on the presentation.
Yeah, if you click, then you go to a slide that it was a surprise for you, but yeah. So roll out the production host, try to fix it, and then execute this program. This is the next step, which is the 8th step. Now I'm going out from all the performance things, CPUs and servers. I'm going to talk about something real that you see people who are traveling, like me, going to see my family, and they use the aircraft or the plane. And then I want to explain one thing. If there's two perspectives here. We are talking about tickets. So we have aircrafts. Let's say you want to go somewhere. Which aircraft is the best for you? Which plane is the best for you? Which type of plane it's the best for you? And then we go, this is the perspective of the user or the guy who bought the ticket. If we talk about the owner, which is the airline, then it's going to be a different perspective, how you see this. The airline, let's say there's a discussion, the Air France or Lufthansa want to buy one of these aircrafts, they will ask the question, which one is the best? And this is performance. Which one is going to perform better? So if you go with Boeing 787 or 747, why? If you go with Concorde, which doesn't, it's not working right now, or you go with the DC-85. So here we have two different perspectives. It's the same way if we go with the CPU, me, who is a consumer of the CPU on my data center, or Intel, how they see things, time to market, the fab, all these things. All these questions are related to performance, but different perspective. Now, if we go with the perspective of the airline, and you have this data. Just see now only actually the left side. You have this data about different companies, different plane or aircraft. The Boeing 777, the speed is 610, the range of 4,630 miles, and the number of passengers or capacity is 375. If you go to the 747, you have this data. The Concorde, of course, is faster, and DC 850 is kind of the slower compared to different other aircrafts. So which one is the best? There's no answer to this question. There's no answer to this question. Actually, there is an answer to, it's loading, I think it's internet. This is performance too. Let's see. Okay. Okay, we'll do it like this. You see it? Okay. I don't know why it's... Okay, the answer to this question is depending on what you are looking for, what you want to achieve. If you would like to go with the speed, then Concorde is the best. If you want to go with a long flight, which means cheaper price for the ticket, it's going to be the DC 850. If you are talking about capacity, which is throughput. Throughput is the first word that I want you to see for performance. If you are looking for throughput, then you go with the Boeing 747. Okay, back to, I think only this slide doesn't want to be, oh, I think there's an internet issue here. Okay. Okay. Okay, the two aspects of performance, it's time and throughput. Time or latency or response time or execution time. Doesn't matter how you explain this, but it's about time. And throughput, it's the task per unit. If we talk about latencies, how long does it take to execute this job? How long is going to take me to, let's say, if we talk about the CPU, how much time this function is going to spend in CPU. This is how we talk. The language is how much time we need to execute this task. And the throughput is how many jobs, how many things that we can execute. This is the difference between the time, latency, and throughput. Now, here we find a performance definition. So the performance is a unit or units of things per second. The bigger is better. If we talk about the CPU performance, the performance of any CPU is 1 upon the execution time of this CPU. And the execution time is, and the CPU is how many instructions multiplied by the CPI, or cycle per instruction, and the time of my cycle. This is the execution time for any CPU. So if we like to increase the performance, we need to reduce the execution time the maximum. Now, what does it mean reducing the execution time? It means that we reduce the instruction or the CPI, cycle per instruction, or cycle. If I ask you this question, what does it mean reducing instruction? Or how we can reduce number of instruction in any application or any code?
Use RAC.
What is it?
Use RAC. Reduce instruction set.
Good. Another type of the CPU, you mean? Instead of CISC, we use RISC. This is really in hardware. Here we are talking about software.
Send less code, have more efficient code, less code to process.
How we can do this?
By optimizing the application.
Optimizing the application, the end user. Let's say we have, and this is what you find in the different high-tech companies. People, they have bad programming.
Yeah.
Okay, if they have bad programming, what's the solution to reduce the number of instructions? So if we would like to execute the code, what's the first thing linked to this execution before, of course, executing in the CPU, but before thinking about the CPU? compiler. So to reduce the number of instructions, we need to optimize the compiler. This is why we have different compilers, and everyone is talking about LLVM, Intel compiler, GCC, and every time we have a new instruction set, AVX, AVX2, AVX512, LLVM, CLang, all these things, because they don't think about how we can help the developers, which is very important, to write really good code, parallelized code, vectorized code, and then they just take the compiler because it's kind of a static thing, and we just inject some libraries to make it more optimized. Good. So if we'd like to compare two programs, X compared to Y, we just take the performance of X and Y, and the N is going to be the difference, or faster or slower compared to the two programs. If I have this problem of comparing performance A and B, the machine A runs a program in 20 seconds, and B runs the same program in 25 seconds. What's the difference? What's the N here? What is it? 20%? It's a very simple question. You just apply this. You.
80%?
Why?
Because it's just 20 divided by 25.
Perfect. Good. So it depends. If you see 20, 25 times faster, or B is 20 by 25 times compared to B. Yeah. Okay, understanding performance. Understanding performance, okay, how are the following likely? This is the first section. This is why I'm asking questions, just to check if you are still with me. How are the following likely to affect response time and throughput? If we are upgrading the machine with a new processor with a faster clock, what's going to affect?
Cycles per instruction.
No, here I'm talking about response time and throughput.
Response.
Perfect. Increasing the number of jobs means that having a single computer service multiple user. Okay? Adding a new machine in the lab.
Both.
Both. Great. Increasing number of processors. Example, in network ATM machines.
Again, both.
Both. Perfect. So if an Intel Haswell CPU runs a program in 8 seconds and ARM CPU runs a same program in 10, how many times faster the Haswell? Tell me.
Why was adding a new machine going to reduce latency?
A new machine reduces the latency because when you take a new machine, we are assuming that the processor is there is going to be faster, which means that the response time is going to be better and the throughput too.
Oh.
So if we add the condition that it's going to be the same CPU, then we just add in the new machine is going to be only throughput, not the response time. So who's going to answer to this question? 8 seconds for Haswell and 10 seconds for ARM. How many times faster is the Haswell?
So again, 80%.
Okay. 8 seconds. Okay. So actually, the question is not really this. The question is it's the 25% faster. But the question is why some people they are buying ARM CPUs in this case? Power and power architecture. Power because everyone knows that ARM is less power consuming compared to Intel. Power architecture. Yeah, which is power? Cost is cheaper, maybe. How the pipeline is going to affect our may performance?
I/O channels send data to the CPU.
But the end user doesn't know about the pipeline. He knows only about this is faster, cheaper. That's it. So power architecture, and the pipeline actually is with the architecture and the cost.
Smaller, portability.
They don't really care. Just buy the CPU. Even smaller is going to be part of the pipeline too. Because
easier to program.
in which way?
In terms of maybe, there are more, tools available to actually carry out all that programming and stuff. And the other might be slightly more complicated.
yeah, a little bit more complicated. But essentially, it's going to be power and cost. Well, actually, for me, it's only cost because power, let's say I don't know ARM, but it's going to be cost. So performance of computers. How we do performance for computer, how we measure performance in computers.
So
Yes, Yari.
going back to your slide before, so you mentioned earlier the importance of the compiler in your performance. So we know that Intel, for example, provides its like an optimized compiler versus GCC. Would ARM provide the same thing? I have no idea. Would that be like another criterion?
Yeah, this is actually a very good question in deep in performance. Yes, this is very important for me as a performance engineer. This is very important to a guy who's going to profile the system. But for developers, they don't really care. For them, they even don't see what's the CPU info in their server. They just care about functionality of their program, how fast it is. Actually, they don't care really about performance and security before production. So when we do the push, which means that we send the update or create a new application from scratch and push it on the server, then they start caring about the performance and then security. Performance, they try to understand what's the CPU architecture. Then for the compiler, yes. For example, if, for my experience, when we talk about replacing or finding alternative of Intel CPU in specific application, it's hard because the compiler is one of the thing. The set of instruction too, a lot of criteria that can maybe make it a little bit difficult to developer to do it, and also from a performance perspective. So how we can compare computers? What we need is a benchmarking. By real application, so running the same application in two different servers. Modified application, which means that adding counters on the application, and then these counters are going to give us the information about how fast is this application in this specific CPU or machine and the other machine, and the kernels too. Sometimes we check running this OS in this server and then running the same OS in other server and see the response time through the benchmarking. So the benchmarking is more about measurement and evaluating the performance of a function. It can be a function, it can be just an operation, or a business relative to others. It can be anything. So benchmarking, we don't only use it for computer science, but we do also benchmarking in other things. We start with the hardware performance. Any questions here? Because we are starting with the second section, which is hardware performance. No question? We go? Okay, hardware performance, essentially I'm going to talk about CPU performance, memory performance, and network, and also disk or I/O. Let's say we have a server here. We care about what's inside, but also we care about the server for performance perspective, how we can open the server easily, how we can plug in the power. All these things are extra, but essentially we are talking about these four things. CPU generation. I'm talking here about server CPUs or Xeon CPUs. Xeon CPUs, just an example. It just doesn't mean that I'm not talking about AMD, any CPU, but this is very good picture actually to see how the generation of CPUs going from a technology of 45 nanometer to 14 nanometer, which is Cascade Lake right now. We have Skylake before, Broadwell with 14 nanometers. Looks like Intel is still going with the 14 nanometers, even though they announced 10 nanometer. But we are a tick with Cascade Lake, and we are doing actually the performance analysis for that. Question? No? Good. So we can see these different generations, and TIC-TOC is the TOC is the new ARM microarchitecture, and the TIC is the new process technology, where we see, for example, Nehalem with Westmere, different technology from 45 nanometer to 32 nanometer. And now we are dealing with Cascade Lake, which is faster in number of cores and frequency. We see this, talking about the frequency. Here you can see the evolution of the frequency. You can see different things, but just look at the green thing, which is frequency going from 1 gigahertz, even less than 1 gigahertz in the 70s, and now we are hitting, in 2019, we are hitting almost the 4 gig. But it's stable from 2000 to 2010, and then there are some presentation here about HPC, that he was talking why we have this stability. So these seminars are really helpful for people who want to really understand how it works for different, not only HPC, but computer architecture and this compute and artificial intelligence as well. Now talking about the CPU, same thing, huge progression, for, same as a frequency for the CPU cores, where when you have more cores, of course, the performance is going to be better, and also when you have more frequency, the response time is better. So everything is connected. We can see from Nihilum with 8 cores going to the 24 cores, Broadwell. Now we are talking about for Skylake 28 cores, and for Cascade Lake it's 56 cores. Special 92, the Xeon 9282 with competition with ARM, with AMD EPIC ROM with 64 cores. And it's 128 threads, which is almost hitting the Intel Xeon Phi with 72 threads. So we see a huge progression of number of cores, which has a huge impact in performance. Back to the spec benchmarks. What we use for our hardware certification, we use the spec. And the spec is the Standard Performance Evaluation Corporation. It's like a neutral company that just report different performance analysis for different CPUs, different hardware, sometimes different vendors. When you have, for example, HP with Dell reporting different CPU performance, then spec is the place where you go and see different performance analysis. Started in spec 1989, now we are at spec 2017. We have 2 types of programs here. We really care about the INT or integer programs, but also there is a float point programs too, where you can see the performance. And the score is very, very significant for us because we can compare different vendors, we can compare different CPUs. For example, AMD compared to Intel through the score, the spec score. This is one picture of how it looks like, different programs, because the benchmark, you have different programs, and every program is doing something. Sometimes it is doing encryption, sometimes it's doing compression, sometimes it's pure compute, sometimes it's vectorized or highly vectorized applications. So it's all about compute, load and store, which is more interaction with memory, and the branch prediction. So these are the programs that tell us what's the best performance in terms of CPU when you compare two CPUs, for example. So here, just a graph where you see 20 cores of Ivy Bridge CPU, the 2670, for 1, 20, and 40 threads, and running different specs, and then you can see the number. And this is the score, and then at the end you have the total score of all the programs of the spec or benchmark, and then we can say that if we have, for example, 200 in this CPU and the 205 in the same CPU or different CPU, then we can say that if the number of cores and number of threads and the frequency is the same, then we might choose the best one in terms of spec score. This is a real graph of running the certification process. So this is the power. So we measure the power, which is very important. And then you can see at the beginning, and you can see the power like hitting almost 350 watt of, I think it's a Sunny Bridge, it's an Ivy Bridge 2670 CPU in HP DL160 Gen 8. And then through only the power, you can see what we are running. So the first step was the spec, precompiled, and then the native for 120 and 40 threads. And then we go to the spec 2006 just to see what's the number between the 2000 and 2006. Back in the time we were doing this, now we are not. And then the good thing you can see when we are building the spec. So it's hitting almost 125, I would say, 125 watt when you are building the spec, and then going back to the 350, and then finishing the certification when we are in the spec and looking at the power at the same time. So here it's the timestamp. So the hardware certification process, as we saw in the previous slide, it's about not only running the benchmark, but also power analysis, memory configuration, and BIOS setting. We see why we care about memory, because it's really connected to the CPU, and the BIOS settings too. It's also connected to the vendor. So when we got a server from HP, we just change some BIOSes, and then we see a huge impact in performance. So it's really important. So benchmark, power, memory, and BIOS setting. But back to the power the server component, where we care about performance and cost too. So money is important too. It's not only buying a cheap server, but also looking at the performance at the same time, and different components within the server. It can be same thing, CPU, network, power, I/O, memory, and also accelerators, which means the FPGA or GPUs. Now, we talked about CPU performance. As I said, it's about the compiler too. So when we do the benchmarking using the spec, we see what's the best compiler to use to get the most optimized or the best performance. The performance of the workload too. Which application? Is it the spec only or real application? And also memory population. So the configuration of memory in the server has a huge impact on your server too. This is one, the Skylake CPU. I just want to explain or show you the details of any CPU. So the CPU has a TDP or power. So when we buy the CPU, we need to see which power we are looking for, between 70 to 205 watt for this specific Skylake CPU. The socket. So usually we use the dual socket in our servers. So it's important too if it's a single or dual socket, or more than dual socket, or more than 2 sockets on the CPU on the server. How many cores? It's really important with hyper-threading technology. The memory is really important. Are we going to use 6 channels, 8 channels, 12 channels, DIMM? And what's the frequency of the DIMM? Because it has a huge impact on the bandwidth, the memory bandwidth, and also the latency. Back to the channels here. The connection, when we have a dual socket, what's the speed between the 2 CPUs? QPI, here we call it the UPI in this specific Skylake CPU. And the PCIe lanes, how many lanes we support, how many per CPU, which is going to give us more opportunity to install or plug other devices, for instance, the GPUs or FPGAs. Now, if we talk about the instructions, because I asked this question about how we can increase or reduce the number of instructions, we have a lot of things in the compiler, but the AVX is one of the things that is very important in each CPU technology. So you can see from Nehalem to Westmere is changing. At that time it was SSE4, and then more for encryption, AE SNI, and then Intel AVX, and Intel AVX2. Now we are at Intel AVX 512 for Intel. And this code, the code size reduction is going to give us less instructions, which means better performance. This is why we care about the AVX in this case. This is the AVX for Sunnybridge and Ivy Bridge, AVX2 in Haswell and Broadwell, and AVX 512 in Skylake Plus, even in Cascade Lake is AVX 512 that we use when we are running the spec benchmarks, for example. For the Spec 2006 benchmarks, you can see that some specific application within the Spec 2006, they really using the AVX Pearl Bench, for example, they is using the AVX2, LibQuantum AVX 512. So if you switch off the AVX 512 in LibQuantum, you can reduce the performance and increase it if you use it. And then you can use different other or external libraries like Smart Heap, which is more helping the memory heap and then getting better performance, which is more software. But when we do the certification, we care about all these components because they are going to give a better score. Let's jump to the memory performance, which is we saw the CPU performance. Memory performance is really important, and it's a limited, unfortunately, it's a limited resource available to the application. And if you don't use it in a really correct way, then it's going to affect huge. It's going to affect really the performance. And for example, the speed for the 1600 mega transfer per second has about 20% of performance compared to the load 1333 mega transfer per second. So when we see application like this, when you allocate application, especially when you are using Java application, you are using application memory, or you are using the memory, and then you use more and more memory because you have either creating more objects. Maybe this will be a memory leak issue, or you are just creating objects because you need them. And this is all about this bad programming of developers. This is why at Verizon we're trying to create like programs how you can parallelize your program, how you can use different parallelization tools or options that can make your program better. Same thing for vectorization too. So this is really affecting the memory, and most of the Java application issues are about memory issues. Garbage collection. It's all about the memory issue, where you spend your CPU doing garbage collection instead of executing the real application. This is what we like to see when we run our application and see the memory. So we use our profiler for memory and see this. This is amazing. This is the bad thing when you just use more and more memory. This is the nightmare for us, and this is actually what it should be. When you run your application, you allocate more memory, which means like create more objects, and then when we don't use them, you have your garbage collection, just cleaning everything. So here, when we create objects, and here where we create more objects, and the memory is consuming more. But what's in between? I just said it.
Garbage collection.
Perfect. So we are doing garbage collection in specific Java application. The memory configuration. So most of the people, they think this is why this developer perspective is going to be different than performance engineer perspective, because if you don't install correctly the memory on your server, if you don't do a right population, it's going to be a big problem for performance. So this is how it looks in the server. This is the DIMMs, the slots where you put your memory DIMMs, and then if you do any problem or any issue, any mistake, either not placing really correctly the DIMM or the bad population or configuration of the memory is going to affect the memory. When we see the memory architecture in terms of connection or connectivity with the CPU, for example, if we take the Intel on the left side, you have the QPI this is a dual socket server, and then you have the two memory channels coming out from the Skylake CPU, and then you have the 6 channels. If every channel has 2 DIMMs, which is the total of the dual socket of 24 DIMMs. And then when you see one of the latest AMD EPYC, then you have this fabric, which is kind of similar to the QPI, and then you have 8 cores connected to each other, and there's a cubical, maybe 3D connection between the 8 cores, which help in the performance. And then you have 4 memory controllers, and then the 8 channels in every side of the CPU, which give us 16 DIMMs in each CPU, a total of 32 DIMMs of memories. So this, just to compare these two things, when you have more memory channels with the right population, is going to increase kind of 33% better performance in AMD with extra 8 DIMMs, 4 memory channels. This is the memory performance where we see the DDRs, DDR1 in 2000 until the DDR5. It's coming out in 2020. And of course, the data rate in mega transfer per second is going to help a lot in performance because you have more memory bandwidth, which means that you're going to get better throughput. Let's go to the I/O now. We were talking about CPU, memory, I/O. The I/O is, I don't know, I need to check time. Are we good?
Yeah.
Okay. So the I/O, you need to keep one thing today. It's to minimize the disk reads and writes. This is the comparison between a RAM where you do a reference and a read, and also on the disk too. So minimizing the disk read and writes is going to help a lot in performance. Always, we say that the reads and writes are expensive in I/Os. And this is one of the profilers where you see the reads and writes in a specific application. And then when we talk about the reads and writes, we talk also about the type of the disk. Is it HDD? Why we move to SSD? And it's also the same thing as the aircraft things. Price, capacity, speed, durability, and form factor, and noise. Well, noise for us, data center, it's not really annoying, but the rest is really, really important. Why we moved from SATA to NVMe, it's about the PCI Express, transfer of data, and enabling the rapid storage. HDD, we are still at the HDD because they are cheap compared to SSD, for example. Now, why we use the SSD? Because if we like to use some specific operating system, how it's going to be fast, even though it's expensive, and now actually the price is going down, and the size of the SSD is going up too at the same time, which is very good. But every server, we care about HDD or hard disk because of the large capacity and the rapid storage in SSD. The mixture is going to be the best word. Next, network efficiency. Also, the first thing that you need is minimize the network latency, or at least repeated amount of the same thing that you are doing processing. For example, here you have a server doing a request. You have your desktop doing a request to our server, let's say Yahoo Mail, doing the processing, and then responding or sending the response to the desktop. This is all about the delay. We don't care about really processing here, but if you want to do a good fast request, and the fast response is going to be by lower latency. At Verizon, we have 10 gig, we have 25, 20, 50 to 100 gig between latency and throughput-oriented applications. We are looking to the next generation with the 5G. Verizon just announced that I think last week in Maryland and DC, they have public 5G. And then we are trying to find the best network, especially the Intel FPGA programmable acceleration for network application, for live video streaming, for virtual and augmented reality, and different 5G application. For GPUs, we work in different projects in deep learning and artificial intelligence projects for ad click prediction, personalization, search, for access for data. We are looking for the next generation mobile search, mail, publisher, and ads, and videos. So the GPUs or accelerators in general and FPGAs are used for power processing, architecture, and programming languages. Also doing the training and inferencing. Mostly we use GPUs for training and FPGAs for inferencing, but we use also the Xeon CPUs for inferencing too. This is one of the projects that we did with Intel for Bcrypt, and if you don't know about Bcrypt, actually it's the encryption login using mail or any application or service at Yahoo, and then we used actually FPGA to accelerate the encryption for using OpenCL, because FPGAs at Intel, it's not like CUDA for GPUs. We use OpenCL as a software layer, and it's supported by Intel Altera FPGA, and the name of the FPGA is the ARIA 10. Now going to the software performance. Any questions about the hardware performance?
What about, you mentioned anything about tensor cores or TPUs that are becoming more available these days?
We use we use the, you mean the Google TPUs? We use the TPUs in cloud. So we don't have TPUs at Verizon, but we use on the cloud. Which application? I don't think I know any application using TPUs for now. Most of our applications, especially for deep learning, we use NVIDIA GPUs or AMD GPUs. The V100, it's also a TPU processing too. So we do a lot of tensor operations using the NVIDIA V100. Yes, Riyad.
So we're talking about CPUs, GPUs, and now with machine learning and deep learning, just to follow up on his question, if we look at a company like Apple, they now in their SoC, they have like a third engine, which is what they call it, the Apple neural engine, I think, that's really meant for acceleration of all these deep learning, machine learning. They use it for their AI, for their facial recognition. So do you see this coming from other like makers like Intel? Or?
Yeah, actually, Intel, they have OpenVINO. OpenVINO is it's a software layer. It's not a hardware. They use for that. They use actually they have a deep learning processor coming out very soon. They have, of course, this FPGA, but more in inferencing. For training, they have a new one. But yes, they have OpenVINO that we use for image recognition. Image recognition is going to replace actually I think it's a image toolkit or something, a vision toolkit or a vision kit that we use for different applications. But yeah, for Intel, they have OpenVINO. For Facebook, they have their own application or software layer or toolkit. Google, same thing. So for software, I know that everyone is doing things. We don't have our proper toolkit or a kit that we use for image recognition or even for speech recognition. We use others. But for hardware, I know for Intel, they have their own processor for face recognition and also image recognition and speech recognition too. Other hardware, I think it's going to be mostly NVIDIA GPUs or AMD GPUs. Okay, software, we are going to talk about monitoring and benchmarking versus profiling. I think most of people, they're confused between what's monitoring compared to benchmarking and profiling. I'm going to try to explain this. Profiling tools, a real issue that we solve. I'm going to show you a real issue that we solve. Actually for the 15, because we have another seminar for the 15, I'm going to try to be more in real application, doing some vectorization profiling too with the real tools. Like this, you see what's as a definition here and what's real and how we are doing it. And I'm going to talk about some performance tools too. So software, if we talk about software, is going to be about code efficiency or algorithm efficiency. Everyone knows about the big O. Exponential, linear. This is the basic things that developers need to know because we always ask if we can do better. If you have a Fibonacci series, you want to do it in Python, you give the first solution, then maybe a recurrent solution, and then if you can do better, or any application or any program that you can do, well, for this efficiency, looks like the binary, the dictionary is one of the best in terms of efficiency with big O of 1. But always think about what's the best thing you can do in terms of algorithm efficiency or a big O. Now I did some survey about programming languages at Verizon. And this is what I found. Most of when I came in 2012, people they were talking about C, C++. I was doing a lot of code optimization for C++ and PHP in general for web applications. And then, from 2012 to 2018, we saw this big jump from C++ application to Java. And mostly it's because of this dynamic memory allocation, or people are lazy to allocate memory in C++. And then after this, try to empty the memory each time. So Java is doing this through the garbage collection. But the problem is when you don't know how to do it, and you just allocate every time memory for your object and create more and more objects, then it's going to be a real performance issue. So we are talking here about almost 95% of developers, they do Java programming instead of C++. We still have some people doing C++, but we can see that the graph is really showing this jump to Java programming. Now, how we do monitoring and profiling, benchmarking, and what's simulating and emulating, and what's the difference between that? Of course, looking at it as Java application. So for monitoring, every big company, every high tech has this monitoring system, internal monitoring system, where you can provide like your software application to detect things like transaction performance, response time issues, CPU utilization, disk space consumption, all the packets on the for the network. This is the monitoring, and then monitoring need to answer to this question, different questions. How many major data centers, for example, at Yahoo? How many servers at Yahoo? This is our internal monitoring system. How many servers with FreeBSD? And how many servers they are using less or more than 10% CPU, because it's important to see what's the load in the CPU. So I was actually going to give you the answer for this, but I thought that it's confidential to share all this data for the monitoring. Now, what's the difference between benchmarking and profiling? Benchmarking is more about competing or evaluating two systems where you have the function operation, and then you just try to evaluate using benchmarks. Profiling, it's about comparing multiple versions of the same program or different functions within the same program, and then see what are the areas that you can actually improve, and also what are the bottlenecks on your application. This is what does mean profiling. So it's more about observing or observation, and then if you are good in analytics, then you are good in profiling. So it's finding and eliminating the waste and wait time and the area to tune and understand the system limits, for instance, the memory, and solve the performance issues, locate the bottlenecks, and build like a modular architecture system application wherever using the profiling. If you want to do profiling, you need to start with something simple and then go to the advanced or the more complicated application or tool or anything. If you are working in Linux, you have a lot of packages that you can use, like top, uptime for basic analysis, where you do observation and finding the bottleneck. And then you jump to something which is intermediate analysis. You can use SAR to specify the subsystem, and also finding the issue if you didn't find it on the first step on the basic analysis. Now for advanced, it's selection. You already have the solution. You just need to tune the application using some advanced tools like gprof, perf, and also vTune. Intel vTune is the one that actually I use a lot in this step. So, of course, more details, more impact. When you use advanced analysis, then you are going to bother the system, especially if you are doing profiling in production, which is not recommended. This is a beautiful performance script that you can start if you would like to start with the performance engineering and profiling, especially. You can hit the CPU by mpstat, and then memory with vmstat, trace for the file system, and the disk I/O with IOstat, and the netstat with the network. This will give you actually a good overview about what's your system and what you are running on your system. Let's get back a little bit in the kernel architecture, because everything is related. If you want to do profiling, you need to have at least a beautiful picture of your kernel of user space and the kernel space, and where you are going to use different tools for different steps or different layers on your system. And this is beautiful actually in each system where you can use and what you can use. On the user space where you have application, of course, you can create your debugger to understand what happened, what are the errors that you have on your system. If you go to the operating system, perf, it's good to profile your operating system. System call interface for the TCP scheduler, the virtual memory. You can use vmstat, dstat, iostat. You have device drivers and then different component of your server in the kernel mode, where you can use all this set of tools to profile your system. Let's get back to the Java and the garbage collection profiler. At Verizon, we use a bunch of tools to profile the Java application and also to profile the garbage collector or garbage collection in general. And the VTune is the more popular with the 47%. Some people, they use the same time, different order, either Oracle tools for garbage collection in Java or Intel VTune for Java. So actually I'm happy that VTune was not supporting Java for a long time, like only C, C++. And we started the project with Intel to create this feature supporting Java, because actually we had the vision that Java application is going to increase, and a lot of developers coming out from school and they're good in Java development, and also maybe because they're trying to avoid allocating memory and Java or JVM doing it instead. Intel VTune, I highly recommend how they call it, godfather of VTune, Gary Carleton, who's a good friend. He's retired right now, but there's a very good a video that it's already in the HPC seminar series. It was a 2000, what is it, 15, 16? Something like this, before his retirement. Yeah. He was here in Stanford High Performance Computing Center. Very good training. And please let me know if you need some training, similar training like this. I got a lot of, I learned a lot of things from him, especially in VTune. Of course, now VTune, we have more features, like for, as I said, for Java, for containers, for VMs, for virtualization or virtual machines, which is going to help a lot of people who are working or want to work in this area. So VTune is a tool that can locate and remove the software performance bottlenecks by collection. So you collect your data, you analyze your data, and then if you are good in analytics, then you can find the area where you can tune the application, tune your code, function, and you have also access to the source code, which is amazing. Honestly, I don't see a lot of tools that can give you access to the source code, C, C++ or Java in the market. Perf, well, it's very similar to Perf. Just Perf is like open source, and then you can use it. But I like it in the way how you can monitor your results. When you collect the data, you copy, or you can even collect remotely, and then you can see all this bunch of data in very beautiful graphs, and it's very, very helpful and very visible, and you can read it easily, not only as a performance engineer, but also as a developer. Yes?
You can collect data remotely from production?
Yeah, you can collect remotely.
What sort of data is it collecting?
What is it?
What sort of data is it collecting?
So it's going to let's say if you have a Java application, you have three types of analysis. And we are going to talk a bit about this later. It's complicated, but three types of analysis. You can get the hotspots, so the three top functions that spending most of the time making your CPU utilization high. The second thing, you can do general exploration, which is very good, and I recommend doing the general exploration as the first step because it's going to give you a very good overview, big, beautiful summary of your system, what's running in your system, different functions that are running, all these things. And then logs and waits. Logs and waits is more about context things that what's happening. And if it's Java application, it can give you even a garbage collection visualization, which is very good. It's very helpful understanding what's the stop word, and what's the frequency of your garbage collector, which kind of garbage collector. And it can give you also the frequency, a lot of things. Like VTune is very, very helpful in this. You have different tabs. You can go top, down. You can see the caller and callee, which is very, very powerful looking at these different functions. So this is how it looks, the VTune. You see the different application. This is the main application and different functions running. And then it can give you where it's running. The red thing is the overhead. The running is the green one. And then the context switches, which is very good in the light green. And then when you click in one of the function, you have all the details here. And then you can see the source code here too. And then it's going to point you at really the function or the loop or where you are spending most of the time if you click it on the top. So we can do this is a small video about how you can use. That's good, because I even make yeah. So you download the VTune from internet, and this is what you're going to do because this will be free for you. And believe me, it's expensive. And thanks to Intel about this, for this. So you do the serial number.
I think the full package is like 3,000.
Yeah, it's really expensive. So you are going to get this for free for 1 year, which is very helpful in terms of performance. So
it's 1 year in support. And you get to
and
use
support.
the software
Yeah.
forever, at whatever version you're at.
1 year for support, but the software.
Yeah, the software continues
lifetime.
working. Yeah, yeah,
License, right?
yeah. It's just at whatever version you happen to install.
Yeah.
So you just don't get the updates. You'll have to pay for support to know if you want updates.
If we want updates, then we will have to purchase that.
Yeah, yeah.
So this is the monitoring.
You pay for support.
And you can install it in your Mac. There is a version for your Mac for monitoring. And then here you have the first window. So here you just open the file that you collected on the server. I'm going to show you what you are going to do in the server. So this is installing the VTune collector. So you have two packages, one for the server, one for your desktop. If you don't want to do it on the server, if you want to do it remotely, you go to the shell, and then you download, of course, the collector, and then you install it, put the serial number, accept all these terms and conditions. Or you can do it, actually, the installation automatically. They have a script, you just run the script, you put your serial number there, and then everything will be running. Here, done. These are the paths that you need to know to use your collector on the server. And then you just start collecting. I'm going to show you one of the instructions or command line to collect data, I think for hotspot. Yeah, start collection, for example, advanced hotspot. This is how you use Amplexi CL, collect advanced hotspot, and the name of your script or the application. You copy the collection to your desktop, and this is how it works. This is a very beautiful summary. CPU usage, how many cores you are using for this specific run. And the green it's better. There it's like you're not taking advantage of different threads or cores in your CPU. Here you have all the functions that are spending most of the time in your CPU. The hotspots are the top ones. When it's red, means that you are not really taking advantage of your resources in general, CPUs and memory. And then you see the details. And every time you click on the function, you have the details. And you can get even the frequency, all the hardware things, and obviously the software thing. Okay.
So this will pinpoint to the place in the code where the optimization needs to be.
Exactly, yeah. If you want to go deep on the source code, then yes, you just click on the function, and then the function will give you the source code, and then give you the region where you need to tune. Sometimes you need to maybe change the kind of library that you use for C++ or Java or whatever. Yeah.
But then that offers assuming that we have access to that.
Yes. Mm-hmm. So you are going to get the two things: the collector and the monitor.
Applications that we have.
What is it?
For own applications, the ones that we create.
Yes. You can find samples too, some example of application that you ran just to see how it functions, and then, of course, there's a huge tutorial and videos about VTune, but we can do actually seminars or even courses about VTune for it.
And so I think something important to note, like there's VTune and there are many other applications that are part of Parallel Studio, but in advance of running VTune, they have this lightweight tool, application performance snapshot, and you can run that first, and that will give you pointers on like which tool to use. You know, so if you're, if it's something system related or memory bound, or it could be communication, like it's MPI, and so APS will make suggestions like on whether you should use VTune or Trace Analyzer and Collector or Advisor or one of the many applications that's in the suite. So that'll just give you a very high level overview, and most times you'll be pointed towards VTune.
Yeah. So this is one of the real applications that where VTune was very helpful. We started from, as I told you at the beginning, the metrics are QPS and latency is one of the biggest enemy for Verizon. We started at 270 QPS, and then we got some developers and the manager of the product coming to a performance engineering group and say, okay, we need to increase this because we are losing a lot of money because of this number of requests per second. Then we used VTune to understand where is the bottleneck, and then also help us. VTune was helping also to tune the application through different code improvements. We moved from 270 to 2,000 QPS. It was a huge successful VTune usage. Also the collaboration with the developers. They were very open to improve the code and use the different or alternatives in terms of libraries for the specific application. It was really helpful. So this is one of the things that every performance engineer is dreaming about. Looking at very low QPS, high latency, going to the best QPS that you can hit, and then it's going to be always a big improvement.
So what's the learning curve like for this?
What is it?
Learning curve, what do you mean?
Learning?
Yeah.
What do you mean by?
The learning curve, how difficult is it to actually, kind of learn, or how easy is it?
Yeah, so to be honest, I started VTune in 2009 or 2010, right? At that time, it was really like a kind of a basic tool. And then with time, Intel is start to improve it better and better, especially in reporting, because actually the biggest issue, how you can share the reports with developers when you finish your collection, and also how to teach developers how they can use VTune, because they have this idea about open source, perf. For them, it's like they're like really staying in the same operating system and do the collection and do all the performance, if they do it, because usually they just do programming, they don't really care about performance. But some people they do performance and use the different tools that I have. Now when you have VTune at the beginning, as any application, anything in your life, you have issues installing it and then going to the next step, which is using the right command lines, instructions, and understanding which one. For example, if you start with the locks and waits, this is not going to help. You need to explore your system, look at the hotspot, and then see what's next. If it's locks and waits, because locks and waits is like between 5 to 10% overhead. Sometimes when I ran vTune to collect data, I find vTune as the first hotspot. So you vTune your vTune, right? Which is not really helpful. So the way how you do it, you need to know, and this I guess is through the experience. But we try to actually help people, me with Intel, because they see that I use this vTune like every day. Means that every time I just report to them some bugs, some new thing that they need to use. They listen to my feedback. Always there's something new. Now we are going to the next step with vTune, where you have your vTune in the cloud, and then you can run it in different servers where they have bottlenecks or issues. So it's the way how you are motivated to learn about vTune. This is the first thing, I think. The second thing is, of course, you are going to find issues. Sometimes it's not working. Sometimes the system crash, and then you need to understand what happened. But I think if you take experience of, or you ask help from Intel, or even me, I can give you a very fast answer, and then see how you can get it or master the tool. Yeah. So yeah, most of people they're like confused when and where I'm going to use vTune, and then this is a very good table where if you go with a snapshot like quick performance analysis, I don't think that vTune is going to be the first step. You need to use some small tools, and the vTune is going to be there's an Intel vTune snapshot where you see the CPU, memory, I/O network. I'm going to show you the picture later, but it's going to help you to see your system and then find one by one where is the issue, which component. Is it the CPU or memory or I/O, whatever. This is for the application, one application running. If you talk about the full system load, where you are maybe in distributed system, or you need to scale out your performance, then you need to go with Intel storage snapshot, the vTune, and do maybe logs and waits, and Intel platform profiler, which is really good because you can collect the data for a long time, like 13 hours, and then see the behavior of your system, and then understand which time you have maybe this bottlenecks or issues, which is very, very helpful. If you go with advanced collection for one application, then Intel vTune general exploration is one of the things that you need to do for CPU and memory. There's more tools, performance tools for hardware, Intel Performance Platform Profiler, Intel Application Performance Snapshot, and for the software you have the Intel vTune for container and Intel vTune for VMs. These are the tools that Intel created, or more features for vTune. And this is the storage performance snapshot I was talking about. So you can see the CPU, you can see the system, memory, network, even the disk. All these things is going to be helpful for you at the first step, understanding where is exactly the issue. Now about power. Power is like also very important performance term at performance engineering, because it's really related to the TCO. If we have higher power, then with better performance, it means that it's a higher TCO. We need to maybe negotiate to get better TCO with better performance and low power. And power, of course, is connected directly to money, and also it's connected to the CPU too. If the one CPU is consuming, let's say, 300 watts of water, of heat or of power, then it's going to be scalable, maybe linear, or even more exponential in different servers in our data centers. These are the tools, the TurboStat. I think everyone knows about it, to collect some data, which is part of the CPU power utils package. And then also Intel has a good tool that, which is the Intel Power Governor. It's a software utility and library that you can use to collect some data, like the power data. Talking about power, now mobile, we really care about performance and power and speed. For the energy profilers, one of the tools that you just connect exactly the same as you see in your picture. Flickr, which was one of the Yahoo application, Tumblr too. you just run Tumblr or debuggable, actually debuggable application here in your tablet or phone. It should be Android phone with Intel CPU. Then you plug it on your computer. You just open the energy profiler and or power analysis, and then you see very good graph like this and different wake up, the reason of the wake up, and different power state, and then the wake up objects too. And then you can play with your debuggable application, trying to tune it to consume better power. For the graphics, you have the graphics performance analyzer. People who are using GPUs on their application on the phone. Also, there is a graphics performance analyzer, very helpful for better performance. Now, how to scale out the performance? Now we are going to another section. Any question about software, power, and mobile?
Sorry, I missed, maybe you mentioned earlier. Is this GPU thing available both for the Windows and the Linux?
Yes. Everything here, even for Mac. For example, vTune is actually available for Mac as a monitor, not a collector. Because usually you collect on the server.
Both as a monitor, collector.
Yeah. Mm-hmm. So when we talk about the scale out of performance, we are talking about how we can scale horizontally or vertically, which means that are we able to increase the throughput vertically with more CPUs and cores and memories, and memory within the server, or create or buy other servers with the different data centers. And this is very connected to the cost. This is why the cost is really important with performance. So it's a big decision of capacity planning. And this is why we call it the capacity planning for different application, different product, different services within the company. If we need to plan a largest server and data center capacity, or do the data center expansion plan with scaling vertically with different servers on our data centers. So really it's a trade-off between, I think this is a natural extension to the cloud performance, because it's one of the solutions if you do scaling horizontally. Virtualization is going to help with virtualized compute and network and storage resources between private, public, and hybrid. Here is also it's going to be a trade-off why we do hybrid. For example, for a seasonal capacity change or a seasonal application like Yahoo Fantasy Sports, it doesn't make any sense if you have a data center just for this application that you run it only for a season of football season, for example. This is one of the examples. So it's going to be about SLA and the elasticity and security as well too. So we need to keep this in mind. Containerization between VMs and containers, where you have, for example, the Docker in containers or any other containers or type of containers, VMs, and the combination of both is going to be the perfect word, because we care about security too, and VMs is offering this, and containers it's not really the case. So what we do is like combine them between both of them, and I can actually also talk about containers. Performance in containers, or even one-on-one containers, and then see how we can build your own container, run application, different tasks, do performance, and in performance actually there is vTune for containers, where you either take vTune as a container itself, or install a vTune in one of the containers to profile your application or container. So here the difference and how we can different in performance. If we like to boost the speed, it's more about containers. If we're talking about security, it's more about virtual machines. I think this is one of the very exciting for me, because I think it's one of the few new articles about how we can use artificial intelligence with performance or performance engineering or science of performance. where we can use one of the deep learning TensorFlow model, which is LSTM, for smart anomaly detection. This is one of the papers we are going to publish internally for one of the conference at Verizon and externally for artificial intelligence conference with performance. So how we can use the data we have for system utilization and memory utilization to detect if this data has anomaly or not. We do it manually. We do some script for that, but we never use some artificial intelligence or a model, neural network, unsupervised the neural network model to detect the anomaly, which is very, very helpful in our data centers. We have a large amount of data and servers. We'd like to create some system to prevent any anomaly in the future. This is why we created this model of anomaly detection. So just to give you an idea what does it mean, so this is 2 graphs of high and low CPU utilization in one of the servers, CPU and memory actually utilization time series. So through maybe months of utilization of CPU and memory utilization, and then how we can detect low utilization of the workload. This is always was a question for us, and we usually do it through our monitoring system manually. And this is why we created this tool or a model through neural network to detect. Actually, it's going to be maybe public in December. Are you looking for a performance engineering job? Yes? This is all about this talk. Or are you interested in performance? It's also this talk. Do you want to learn about performance? Is it your life professional thing that you want to do? Yeah. So actually, people they think that and they are maybe they do mistakes between software engineer and performance engineer, which is 2 different things. You need to know about software, but also you need to know about hardware. You cannot be expert in the software and you are a good performance engineer. This is why you need, first you need to do the system architecture, the CPU memory, the Hennessy and Peterson book. This is going to be a similar thing as my career. You don't need to do research. I did research because I loved research and I still love research. I love also teaching. You need to know how to develop application in Java and Hadoop. Not an expert, but a general understanding of software. You need to be good in cost and TCO or trade-off things that you don't need, and optimization, good in analytics, but perfection is bad. You don't need to be perfect. Thank you.